Okay, here's another good optimization problem. And every one we've done so far, we're trying to optimize on some closed interval. So the extreme value theorem says you know you're going to get a maximum and you know you're going to get a minimum someplace on that interval, possibly at the endpoints. In this case, we're not going to have a closed interval, a closed and bounded interval. We're going to have an unbounded interval. So we're going to have to use we're going to have to use first derivative test to prove that we did in fact find the minimum, the global minimum. Okay, so pause and read the question. Hopefully you've done that. All right, so we got ourselves some kind of box. Now we know we have a square base. I'm going to call both sides down here x, and I'm going to call the height y. You can call them whatever you want. That's what I'm calling. Then volume would be x times y, x squared y. And I'm told that my volume is 216 cubic inches. I want to max or minimize the surface area. So surface area, we have an open top, so this top doesn't exist. I've got 5 sides. Surface area is just all those sides added up. So I've got the bottom here, he's x squared, and then all 4 of these sides around will all be x times y in area. So there are all 5 sides. We don't have a top. Otherwise, I'd have a 2x squared. This is who I want to minimize. We don't know multivariable calculus. We don't know how to take the derivative of this. I need to get this in terms of one variable. So I need that y to disappear. So I'm going to have to use this extra information to say y is 216 divided by x squared, and then plug that in there. So surface area as a function of one variable, x, will be x squared plus 4x times 216 over x squared. And then we can clean that up a little bit. 4 times 216 is, I don't even think I bothered writing it out. Whatever that is, 4 times, oh yeah, I did, 864 over x, because one of the x's cancels there. Now, what's my domain? All I know, the only restriction here is that x has to be greater than 0. It can't be equal to 0 because we're not defined there. My domain is 0 to infinity. So we have this unbounded open interval. Extreme value theorem will not apply. All right, we take the derivative. Derivative of x squared is 2x. That guy you want to think of as 864 times x to the -1 power. Then you'll get -1 times 864. And then this x, that -1, will drop down by 1 and become a -2. So the derivative will be 2x minus 864 over x squared. I want to find all my critical values by setting that equal to 0. I already know I have a point that'll have to go on my sign chart. X is not allowed to be 0. X can't be 0. I want to find where this whole thing equals 0. Okay, and we could easily solve that, get this negative guy to the other side. Multiply the x squared up, divide the 2 over, you get x squared or x cubed equals half of 864 which is what, 432. So x is the cube root of 432, which does simplify. You could check this on your own. That is 6 times cube root of 2. Now, this is a possible minimum. That might be the maximum. We don't know. I want to minimize surface area. This might be a local maximum, might be a local minimum. We don't know. And I can't just plug in my endpoints because my endpoints don't exist. I don't have any endpoints. So we're going to have to do a sign chart and convince ourselves that that is in fact a minimum for the derivative. So we're going to put on here every place where the derivative equals 0 or does not exist. So 0, because derivative did not exist there. And then 6 cube root of 2. And just remember the derivative here, let's rewrite it, was this. 2x minus 864 over x squared. Now, all I care about is positive or negative. That's all I care about. So I'm going to pick any x value in here. I'm going to pick 1. I can do this in my head. 2 minus 864, that's a negative. That means the function is decreasing from 0 to here. In this region, the original surface area is decreasing. And then I'm going to pick a value over here, and I'm going to pick something giant, 1,000. 1,000 squared is huge. This fraction is going to be small. I'm going to get 2,000 minus something small. This guy's going to be bigger than this one. Like, plug it in your calculator if you don't just see it. But anything over here, this one's going to be bigger than this one. I'm going to get a positive number for the derivative, which means the function is increasing. Forever. It keeps increasing forever. So the graph comes down and then goes back up and keeps increasing. Now, it may be increasing to some maximum value. It may increase to infinity. I don't care about that. All I care about is this is obviously a min right there. So now we know the surface area is minimized at x equals, what was it, 6 cube root of 2. And the minimum surface area was, well, whatever that is. So that would be 6 cube root of 2 squared plus 4 times 216 over 6 cube root of 2 squared. Nope, not squared there. So that's x squared plus 4 216 over x. So whatever that number is. All right, and that's a good place to stop.